Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence. Today, we're diving deep into something that's been causing quite a stir in the AI community: reasoning enhanced language models, specifically the EXAONE Deep project. It's a fascinating area, right? Trying to get these language models to actually reason, not just regurgitate information.
Absolutely. EXAONE Deep is really pushing the boundaries of what's possible with large language models. I've been particularly impressed with the scale at which they're operating and the data-driven approach they're taking. It feels like we're getting closer to genuine AGI through sheer computational power and vast datasets.
I'm a bit more skeptical, to be honest. While the scale is impressive, I'm not convinced that just throwing more data at these models is the key to unlocking true reasoning. It feels a bit like brute force intelligence, and I worry that we're missing some fundamental principles of how reasoning actually works.
I tend to agree with you there. It's like we're building these incredibly complex systems, but they still lack a certain grounding in reality. They can manipulate language, but do they truly understand the concepts they're talking about? It feels like they're operating in their own computational space, divorced from the physical world.
That's a really interesting point, Donald. This touches on something I've been thinking about a lot lately. How do we bridge the gap between the computational power of these models and the actual mechanisms of the human brain? Because, we're trying to build intelligent machines. Shouldn't we be looking more closely at the only example of intelligence we know exists?
Well, I see it slightly differently. While understanding the brain is undoubtedly valuable, I think EXAONE Deep's approach of focusing on enhancing language models with reasoning capabilities is a distinct path toward AGI. The sheer efficiency of scaling these data-driven models might actually get us there faster than trying to reverse engineer the brain. It's like, we learn to fly without perfectly copying birds, right?
But isn't that analogy a bit flawed? We understood the principles of aerodynamics, which are fundamentally different from flapping wings. With deep learning, we're essentially just mimicking the output of intelligence without understanding the underlying principles. And that's why I think we need to be focusing on neuro-symbolic approaches, combining the strengths of neural networks with explicit symbolic reasoning.
Yes, and that's where the spatiotemporal aspect comes in, at least in my mind. These models operate in a kind of abstract space, but the real world is fundamentally spatiotemporal. If we want them to truly understand the world, they need to be able to reason about space and time to understand how things change and interact. They need to be able to translate between different coordinate representations, just like we do effortlessly.
Exactly. And that's where I see the potential for bringing in neuroscience. We know that the brain uses different regions to process different types of information, and that these regions interact in complex ways. What if we could map those interactions onto the architecture of a language model, creating a system that's not just processing data, but actually reasoning in a way that's analogous to how the brain does it?
But how would you even go about doing that? The brain is incredibly complex, and we still don't fully understand how it works. Wouldn't it be more practical to focus on improving the existing deep learning architectures and scaling them up even further?
That's like saying we should just keep building bigger and bigger steam engines instead of trying to understand thermodynamics. At some point, you hit a wall. I think we're already seeing the limitations of deep learning when it comes to true reasoning. It's good at pattern recognition, but it can't handle abstract concepts or make reliable inferences.
Right, and that's where the coordinate systems come back in. Take something as simple as throwing a ball. We unconsciously calculate the trajectory, the speed, the spin, all in relation to our own position in space and time. A language model can describe the event, but it doesn't understand it in the same way because it lacks that fundamental spatiotemporal grounding.
So, thinking about EXAONE Deep specifically, they're focusing on enhancing language models with reasoning capabilities. Now, Otto, you mentioned being impressed with their scale. What are some specific aspects of their approach that stand out to you?
Well, first off, the sheer size of the model and the data set they're using is remarkable. It allows them to capture incredibly complex relationships in the data. And they're also using some clever techniques to improve the model's ability to handle dynamic reasoning tasks, where the relationships between entities change over time. That's a crucial step towards building more robust and adaptable systems.
But how are they actually representing those relationships? Is it just implicit in the weights of the neural network? Or are they using some kind of explicit symbolic representation? Because if it's just implicit, then it's going to be very difficult to understand why the model is making the decisions it's making.
That's a fair point. I need to dig deeper into the underlying mathematical and computational models to see how they're handling that. But even if it's just implicit, the fact that they're able to achieve such impressive results with deep learning alone suggests that there's a lot of untapped potential in this approach. Maybe we don't need explicit symbolic representations after all.
I'm still not convinced. It's like, imagine trying to build a map of the world just by taking a bunch of random snapshots. You might get a general sense of what things look like, but you wouldn't be able to navigate or understand the relationships between different places. You need a coordinate system, a way to organize the information in a meaningful way.
Right. And that's where I think we can learn from the brain. The hippocampus, for example, is crucial for spatial navigation and memory. It uses things like place cells and grid cells to create a kind of internal map of the environment. What if we could incorporate similar mechanisms into our language models, giving them a more grounded understanding of space and time?
That's exactly the kind of neuro-symbolic approach I'm talking about. We need to be looking at how the brain represents and manipulates information, and then trying to replicate those mechanisms in our AI systems. It's not about just mimicking the output. It's about understanding the underlying principles.
But wouldn't that be incredibly difficult? The brain is so complex, and we're still only scratching the surface of understanding it. It seems like a much more efficient approach to just keep scaling up deep learning models and see how far we can get.
That's an interesting idea, but how would you even validate such a model? How would you know if it's actually capturing the subjective experiences of the people it's supposed to be simulating? It feels like we're comparing apples and oranges when one is a computer program and the other is a human being.
Exactly. That's one of my biggest concerns with this whole approach. It's anthropomorphizing these models, assuming that they can somehow understand human experiences just by processing language. We need to be much more careful about how we interpret their output, and we need to be developing alternative approaches to model human subjectivity.
But isn't there value in trying to quantify subjective experiences, even if it's imperfect? Comparing ChatGPT's responses to social surveys could reveal crucial insights into the strengths and limitations of each approach. Maybe a combination of both can yield a more comprehensive model.
Yes. And thinking about the temporal dynamics, social surveys provide a snapshot in time, whereas ChatGPT can generate text that evolves over time. But that's just text. To really get at the underlying human motivations, we need to consider the neurobiological substrate. Can we somehow incorporate neurobiological priors, like the timing and location of neural firing, to improve the model's understanding of human motivations?
That's the coordinate transformation problem again. How do we translate between the physical world of neural activity and the abstract world of language? It's like trying to build a bridge between two different universes.
Okay, I'm starting to see the appeal of the neuro-symbolic approach, but it still seems incredibly challenging. What specific computational models in neuroscience could actually inform the design of more effective reasoning capabilities in EXAONE Deep?
Well, for example, we could look at models of working memory, which is crucial for holding and manipulating information during reasoning. Or we could look at models of decision-making, which often involve integrating information from different brain regions. The key is to identify the specific neural mechanisms that are responsible for reasoning, and then try to replicate those mechanisms in our AI systems.
And how can we ensure that these models are not just pattern-matching machines, but genuinely reasoning and learning? That's where I see the potential for incorporating hierarchical structures, similar to how the brain organizes information. By creating a hierarchy of representations, we could allow the model to reason at different levels of abstraction.
So, instead of just feeding in raw data, you'd be feeding in structured information that's already been pre-processed in some way?
Exactly. And that's where the symbolic part comes in. We need to be able to represent knowledge in a way that's explicit and interpretable, so that the model can reason about it in a logical way.
And that knowledge needs to be grounded in the real world, in space and time. The model needs to be able to understand how things change and interact, to reason about cause and effect. It needs to be able to translate between different coordinate systems.
Right, so thinking about future research directions. Otto, from your perspective, focusing on the data-driven approach, what are the key areas that need further exploration?
I think we need to focus on improving the efficiency of deep learning algorithms so that we can train even larger models on even larger data sets. We also need to develop better techniques for handling dynamic reasoning tasks and for ensuring that the models are robust and adaptable to new situations. And we need to find ways to measure the objectivity of the model's responses so that we can identify and mitigate biases in the training data.
From my perspective, we need to be focusing on developing more principled neurosymbolic algorithms that can combine the strengths of neural networks with explicit symbolic reasoning. We need to be looking at how the brain represents and manipulates information, and then trying to replicate those mechanisms in our AI systems. And we need to be developing alternative approaches to model human subjectivity that don't rely on anthropomorphizing these models.
I think the key is to find a way to incorporate spatiotemporal information into language models so that they can truly understand the world. We need to be developing algorithms that can translate between different coordinate systems, that can reason about space and time, and that can understand cause and effect. And we need to find a way to ground these models in the real world so that they're not just operating in their own computational space.
And from my perspective, the most exciting direction is to bridge the gap between the computational power of language models and the mechanisms of the human brain. This means incorporating neuroscientific insights into the design of AI systems, understanding the dynamic interplay between brain regions, and mapping complex neural pathways onto AI architectures. We need to think about how to inject neurobiological priors, like the timing and location of neural firing, to improve our models. This is much more than simply throwing data at a problem.
That all sounds incredibly ambitious, but also incredibly important. I think we're at a critical juncture in the field of AI, and the choices we make now will determine the future of the field.
Agreed. It's a fascinating and exciting time to be working in AI.
Absolutely. The potential is enormous.
Well, that brings us to the end of our discussion on reasoning enhanced language models. It's clear there's a wide range of opinions and approaches, but that's what makes this field so exciting. Thanks for joining us on Cognitive Spirals, and we'll see you next time.